cliches of mathematics that think are wrong. Anyway, I wanted to talk about this thing, which I tried to draw not very successfully. Let me start you out. We'll come back to my drawing in a second. You know what the Cantor middle third set is, right? Okay, the Cantor middle third set, in case you forgot, is you take the interval 0, 1. And you take away the open middle third. So the points at 1/3 and 2/3 remain. And then you take away the points between 1/9 and 2/9, and between 7/9 and 8/9. So the stuff that's gone here, I'm shading in helping. And then I'll just scrap the drawing up if I try to do the 27th. But you can see you've got 4 little subintervals that are remaining. And you take the middle third away from those. And that will be 1/27th of a unit long. At every step of the construction, I drop down by a factor of a third. So the first one is a third away, the next one is 9ths, the next one is 27ths, right? And we prove that the total length, the total measure that is taken away by this process is 1, right? So whatever is left, and there is something left, oddly, is an uncountable set that is nowhere dense. There are no intervals in it. There are no intervals in it because there's always a dyadic fraction that has some power of 3 in the denominator that you could put in an interval, and then you would be taking it away. So if you claim that the Cantor set contains an interval, I claim, no, it doesn't. You see what I'm saying? You know, you just shrink the scale down until you have a middle third that gets taken away inside the interval that you've specified. And then you must admit that no, that interval wasn't in the set because the middle third is gone. So it's a peculiar beast. I don't even know how to. You can understand it intellectually, but it's hard to understand it intuitively, emotionally. It's a thing that you just keep shooting holes in, and there's lots of stuff left, but it's all spread out in a funny way. There's no intervals. It's nowhere dense. It's what the Bayer theorists call a rare set, eager set. Nowhere dense. No interior. A nowhere dense set, the interior of the closure is void. So, since at every step of the game, a set in the Cantor sequence here is compact, and if we intersect up all these compact sets, we get what's left, and the intersection of an arbitrary number of closed sets, these are compact and it's closed, is closed. And since they all lie in the interval 0, 1, which is compact, the Cantor set is closed. Compact, nowhere dense. No intervals inside, no interior. It's already closed. So there's no interior. Weird set. Okay. And we showed, or maybe we didn't show, but you can show this, that the points that survive, if you express them as ternary decimals, are precisely those that have no ones in their expansion. And you can do the Cantor diagonalization procedure to show that if you think you have a palatable list of these things, you can always diagonalize and find one that's not on the list, hence by usual argument for one column. And now we'd like to take this crazy set, do the following thing. Here's one. I would like to construct a function that is key to the Cantor set. And here's what I'm going to do. Remember, the middle third is taken away. So from 1/3 to 2/3, I'm going to give my function the value 1/2. Okay? And then from 1/9 to 2/9, I'm going to give it the value 1/4. And from 7/9 to 8/9, I'm going to give it the value 3/4. Can you guess? As I go from 227, no wait, how many 27ths is this? This is a ninth. So as I go from 1/27th to 2/27ths, what do you suppose the value of the function is going to be? 8. Yes, sir. 8. And then as I go from, oh, geez, how many 27ths is this? That's 3, 6, 7 27ths to 8 27ths, right? 1/8, 2/8, 3/8 maybe, right? Well, you get the picture, how this is built. Okay. And I continue in that fashion. I won't crap up this drawing because it came out better than I thought. but I tried to draw this neatly. If I define approximates, so I take away the middle third, and above the middle third, I let my function be 1/2, and then linear otherwise. As Burke says, you make it linear otherwise. So this is connecting the dots. A monkey can do this. A monkey's doing it right now. There you go. So that's what I call C1, the first approximate to the Cantor function. Okay, and then here's the 1/4, 3/4 thing. C2, the second approximate, will be linear to the plateau, and from plateau to plateau is linear, right? Plateau to plateau is linear. Here I've got, somehow, even though this is bigger, this looks better. So I would be, the third approximate would be this. Okay? That would be C3. And so forth. Okay, now, the CNs are continuous. I claim that the CNs converge uniformly to this thing we're calling the Cantor function, which is it's the pointwise limit of these, and the convergence is uniform. Which means by that theorem, is the Cantor function continuous? Is it? Why is it not? Right? Uniform limit of continuous functions is continuous. Well, all these babies are continuous. And all we have to do is show they converge uniformly. But first, this is an exercise in Burke. Just to get a little familiarity with this. Let's calculate the Cauchy integral from 0 to 1 of the Cantor function. I think it's easier than anything else. Okay. Work with me here. This is what I'm going to do is drop. That has length 1/3 and height 1/2, right? So it's 1/3 times 1/2. All right, now we never come back to this rectangle. Shade it in and throw it away. Put it in the hopper. Go find the next tallest ones. Well, look. One of them is 1/4 high, the other is 3/4 high. The average height is 1/2. And the total measure is 1/4, or a 1/3 plus a 1/3, right? No, a 1/9 plus a 1/9. I'm kidding. A 1/9 plus a 1/9. Huh?
Like, how did that fit 1/3?
It's not. It's not. So it's 1/2 times a 1/3 plus the average height. I'm saved because it's 1/4 on a 1/9 and 3/4 on a 1/9. So that's the same as being 1/2 on 2 9s, right? what's the next, how many and how tall are they? Well, this is an 8, 3/8, 5/8, 7/8. There's no overlap. I haven't covered those before. It's new territory, right? What's the average? They're all, those values are taken on sets of measure 127. So I have 427s with an average height of 1. So I think I would like to add 1/2 times 427. Okay, now how does this series go then? Apparently it's 1/2, and then what would you get? Yes, 8/81, right? So the integral I is going to be